let me mention that this is joint work with Branko Dragovic, Zoran Rakic, and Jonas Markovic. And at the beginning, we have this is a quick reminder about some great cosmological discoveries from the last century. And this is astronomical conference. I assume that most of the people here know that very well. So, well, there is those astronomical discoveries raise some questions that Einstein theory of gravity is not in perfect agreement with observations, and there is basically two approaches to solve the problem. One is to assume that the Einstein theory of gravity is valid for the universe on the whole scale, on the scale of the whole universe, and that requires some additional matter that we call dark matter and dark energy. Or the other approach would be to modify the theory itself. That doesn't eliminate the possibility for some additional matter, but maybe in some smaller quantities. Here we have the standard equations of general relativity, and I will assume for the whole talk that speed of light is equal to 1. If we assume for the moment that general relativity is the gravity theory that describes the whole universe, then the percentages that of the baryonic matter and dark energy are given here. This is data obtained by the Planck mission. And what we see is that over 95% of the universe is on the dark side, so we don't actually know what it is. And as we know, dark matter is responsible for orbital speeds in galaxies, and dark energy is responsible for the accelerated expansion of the universe. Also, the validity of the general relativity as a theory for the whole universe is not established yet. Also, dark energy is just a theoretical concept so far. And of course, there is a problem of the singularity at the very beginning in the Big Bang. All that leads to the possibility of modifying the theory itself. Here we have the Lagrangian of the Einstein theory of gravity, and of course there is almost infinite number of possibilities how to modify this Lagrangian and obtain some modified theory. The two most interesting possibilities are f of r modified gravity and non-local gravity. I will talk mostly about this later possibility. And the non-local gravity assumes that instead of only scalar curvature r in the action, we have some function that contains scalar curvature, of course, and this D'Alembert operator, which is basically just a contraction of the connection, light-theta connection. And for this talk, I will assume this kind of modification. So this is just standard Einstein-Hilbert term, plus the modification is in this form as two monomials, and this non-locality. So this D'Alembert is included as an analytic function here. Also, we assume Friedman-Robertson-Walker metric with all three possibilities, so open, flat, and closed space. And first of all, we have equations of motion that are given here on this slide. And as we know, Friedman-Robertson-Walker metric gives us the possibility that instead of 10 equations here, we have only 2 linearly independent ones. And these are those 2 equations. So this is the trace equation, and usually 0, 0 is taken. Okay, now to solve the solutions, we need some kind of ansatz here, and I will assume the most simple one. So assume that scalar curvature is a constant. And after some suitable change of variable, we obtain a second order differential equation, linear, and we obtain the solutions in the form of, if this constant is positive, as a linear combination of exponential functions. If this constant is negative, then a linear combination of sine and cosine. And if r is equal to 0, then we obtain some quadratic function in cosmic time. When we put that into equations of motion, we obtain these 2 equations. And one can observe that the only constant, only parameter that is constrained here is at 0. So we have 2 equations for one variable, so they have to be compatible. And in order to be compatible, we have this equation here. And that condition. Now I will analyze the first case. Let's analyze this condition that R0 plus 4R00 is equal to 0. And that will restrict possibilities for our parameters sigma tau and k. So we have 3 conditions depending on the sign of R0. And now I will analyze each of the cases separately. So for R0 less than 0, we have, after some suitable change of parameters, we can introduce the scale factor in terms of this absolute value of the cosine function. So we have periodic solutions, but it is also, it has singularities at point. So that is for k equal minus 1. For k equal plus 1, we obtain that a squared is negative, so there is no solution. So for k equals 0, now let's turn to 0 case. And then for k equals 0, we obtain constants for a, so Minkowski solution. For k is different from 0, we obtain this kind of expression for a of t, that's the Millman universe. If R0 is positive, finally, again with some suitable change of parameters, we obtain that scale factor is a cosine hyperbolicus this expression. And for k equal minus 1, we obtain sine hyperbolicus, of course, with some absolute value. Okay, the other case, so everything, this expression can be 0 as well. We have 3 possibilities. Obviously, if p plus q is greater or equal than 1, then we have only one solution, R0 equal to 0. If the sum of these 2 parameters p and q are 0, then there is no solutions. And finally, for these 2 values, this is this one specific value that can solve this equation. Finally, for the second part of the talk, let me switch to the perturbations around one of those solutions. So as a background, I will consider this scale factor, so the Sitter universe. A of t is e to the 1 to t. And for the consideration of perturbation, it is more convenient to use conformal time instead of the usual cosmic time, and it is defined by this relation here. The metric is transformed into this expression, and the scale factor in terms of conformal time is proportional to 1 over tau. Perturbations are in general given by, of course, I will consider here only scalar perturbations. In general, one can consider vector perturbations and tensor perturbations as well, but they're not very interesting in cosmology. And scalar perturbations are given by this matrix here. Of course, we have 4 scalar functions here, phi, psi, d, and e. And what is interesting is that by the appropriate gauge transformation, one can make 2 of those 4 functions equal to 0. So instead of some 4-dimensional space, we have really a 2-dimensional space of perturbations. And of course, it is convenient to find some gauge invariant variables. And the most convenient choice is this one, so big phi and big psi. Okay, these are some technical results here. And when one perturbs the equations of motion, we get expression like this with some new notation here. And of course, we first turn to the trace equations, which is expressed as some operator u here that acts on the perturbation of the scalar curvature is equal to 0. And to solve this equation, we turn to the Weierstrass factorization theorem. And of course, we assume that gamma is an entire function, and that we want only simple roots. We don't want multiple roots here. Of course, to solve this equation, this is an eigenvalue problem for this box operator. And if we have some eigenvalues omega I squared, its eigenfunction would be given in this form, where these functions j and y are Bessel functions of first and second kind. When we express everything in terms of the potentials phi and psi, we obtain those 2 equations, and from those 2 equations it's very simple to express their sum and their difference. Of course, what the asymptotics of the Bessel functions tells us is that phi and psi are bounded if this condition holds, and we are left with conditions of this form. So in principle, we can solve this explicitly, analytically, for these values of p plus q, but of course we can solve it numerically for any value we want. And the necessary condition for the stable solution is given by this expression, and it immediately yields 2 conclusions: that if p plus q is 0 or p plus q is 2, there is no stable solution, while p plus q equal 1 requires that the cosmological constant is negative, and then this parameter at 0 is as well negative. Well, these 2 last equations can be rewritten in even more simple form, like this, with this notation here. And unfortunately, this looks very simple, but in physics terms, it is unclear what it physically means. And these are some references.
Okay. Thank you. We have time for one question, if anybody wants to ask. Until someone asks a question, I can just give you a comment which I always give to Professor Ankic. And instead, for us astronomers, it would be very interesting if you, instead of assuming Friedman-Robertson-Walker method, find a vacuum solution of your field equation. So do not assume metric, but try to find the metric tensor from your field equation. And then you can derive the weak field approximation and obtain some Newtonian potential, which we can then apply test to see is your gravity valid or otherwise it looks like some theoretical concept which looks interesting, but we do not know if it works actually. This from gravity. So just in that sense I have a comment. Any other comment or question? If not, let's thank Ivan again. Last session in this conference. Let's thank all speakers.